Hey, well, this is video 2 of the Earth unit, and as I mentioned before, the Earth unit could be 300 videos long, but this is not a geology or geography or whatever class, and so I want to actually speak mostly about Earth in the other planet videos when I do sort of comparative planetology. I compare the other planets to Earth. Because we know so much about the Earth. So I'm hoping I can finish Earth in this video and then move right on to the moon in the next video. So let's see how I do. Alright, so we know a lot about the interior of the Earth. That's because we don't like earthquakes. They damage our homes and infrastructure and hurt and kill people, cause tsunamis. It's not good. So we study them a lot you know, just to really know them and how they affect us and how to maybe prevent as much damage as they cause. So we know a lot about earthquakes, and because of that, we've actually figured out a lot about what goes on inside the Earth. Um, we have a pretty good idea of what the inside of the Earth looks like based on the fact that when there is an earthquake, the energy travels in waves through the Earth, and what we know about how waves travel through different mediums tells us a bit about what's going on inside. So when there's an earthquake, there's two types of waves. They're called P waves and S waves. Often stands for primary or pressure waves. S stands for secondary or shear waves. Just a very quick overview. Pressure waves vibrate in the same direction as the wave travels. So if the wave is traveling from here through the Earth, then the wave vibrates like this. It's a compression wave, and sound travels like that, actually. Whereas the S waves, if they're moving from here out, they travel perpendicular to the direction of motion. So they would go. See that? Pressure waves travel this way, and they vibrate this way. S waves travel this way, but they vibrate perpendicular. And without going into detail about why, S waves cannot travel through liquidy materials. They travel through solids, whereas pressure waves can travel through liquidy materials. And so, based on the fact that um, pressure waves will diffract, all waves diffract when they hit mediums of different density. You might have learned that in physics or chemistry, maybe. All waves, light does it. When you stick a pen in water, it looks like it bends, etc. So this is no exception. The P wave, when it hits a liquidy material, will refract. In other words, bend. So you got a wave going, and then bends, and then bends again. So we can calculate. We have like seismographs all around the world, and when there's an earthquake here, we can use the data from all of these seismographs to paint a map of how the P waves must have traveled. In addition to the fact that S waves won't go through liquidy material, so there's like they call a shadow zone where you see S wave, 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 no S wave here. That must mean that there's some sort of liquidy material, and that has allowed us to map the inside of our Earth and determine that there's liquidy cores, a liquidy core, and a non-liquidy sort of solid slash semi-solid mantle, depending on where you're at. And we think we know the size of these pretty well, and you can see them here. No need to memorize that. So that's what's going on deep inside, and then we got the outer layer of the Earth's hard parts called the crust, which is made up of some other layers that I won't go into. But what is important is the fact that our crust is mobile. Our crust is broken up into different sections, often called plates, tectonic plates, and they move around slowly, that is, over time. And these arrows kind of show you the direction of motion. So the Earth as we see it now, North America, South America, it wasn't always that way, and it won't always be this way. Um, I got a short little video here that kind of shows you what the Earth might have looked like in the past, based on fossil evidence, based on just kind of looking at the shapes and be like, oh, this kind of big bump looks like it would have fit right in Africa here, etc., etc. We paint this picture. Obviously, can't be 100% accurate, but it's probably pretty good. Here, North America's breaking off. The split between South America and Africa here. Look at India. And he's like, see ya, I'm going up here. It's pretty cool. Australia's saying, it's too cold down here for me. I'm going up. You can rewind that as much as you need to check out, that in more detail if you're interested. Oops. But yeah, so the plates are moving, and they're moving on a sort of semi-solid, what's called mantle. This layer here, so kind of like almost like little islands on an ocean of sort of semi-solid rock. But again, I'm not going to go into too much detail on this, because if you took a geology class or geology class, you would go into extreme detail about it. If you take the overall density of the Earth, which we can gather through other means such as orbital properties and how the moon rotates around the Earth, etc., then the Earth has a certain density. If the Earth was uniformly dense, then we would tell, because the density of the surface materials would be the same as the overall density of the Earth. But it's not the case. The average density of materials up here is less dense than the average density of the entire Earth, which must mean that it gets more dense as you go toward the center. So chances are it's really dense in the inner parts of the Earth, and probably early on when the Earth was young and maybe completely molten and liquidy, all the heavier, say, metals and other heavier elements would have sunk, because gravity would have had a larger effect on them, in one sense, and the Earth would have differentiated into sort of metallic-y core and less metallic-y upper parts. Seems like so far plate tectonics are somewhat unique to Earth. We don't really see them on Venus, don't really see proof of them on Mars, and definitely not Mercury. Some of the moons out in the outer planets, possibly, but probably not. So it seems sort of unique to Earth, which is pretty interesting. But makes you wonder what was different about the Earth's growth or life cycle compared to the other planets. Anyway, because Earth has a liquidy metal dense core that probably can, this is probably so dense that it's just solid even though it's really hot. It can probably like spin around inside this liquidy outer core. There's some physics going on here which basically you have moving electrons that create a magnetic field, and so it's often called a dynamo effect. But probably because of the Earth's quick rotation, 24 hours a day, and the fact that the inner core is rotating with respect to the outer core, we get a nice magnetic field, and it's a good thing, because this magnetic field protects us from much of the sun's harmful solar wind. The sun is constantly shooting out high energy particles, high radiation particles. That's very damaging to life, and so if it wasn't for this magnetic field, a lot of these particles would bombard the Earth. And it's thought actually that the magnetic field switches its polarity every so often, and there's some evidence that mass extinctions coincide with this flipping, meaning when it flips, it probably gets weaker, and then flips gradually over time and gets stronger and stronger again. So as it's getting weaker, the current life form on the planet at the time can't really handle it, and a lot of species die because of it. But yeah, so as we talked about with Venus, Venus doesn't have this magnetic field probably because it rotates so slowly. It's a good guess that the inside of Venus is probably pretty similar to the Earth because it's of similar size, but because of the slow rotation rate, it doesn't really have this dynamo effect, this relative motion of the inner core with the outer core. And finally, last slide before the moon, so I think I'm going to make it. This is actually a good tie-in to the moon unit. The moon is our friendly neighbor. It's big. When you compare the size of the moon to the Earth, no other planet in the solar system has this same relative size. Jupiter is huge. Jupiter and its moons are teeny, 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 teeny. Even the biggest ones are teeny. Same with Saturn. Saturn's huge, and its biggest moon is teeny. Earth is tiny, but if you compare the size of the moon to that of the Earth, it's not quite half as big, but it's close, and it's much bigger compared to the Earth than Jupiter's moons are compared to it, and vice versa. So that's a rarity, and so the moon has a pretty big impact on us, both gravitationally and in other ways too. It pulls on our oceans. It actually pulls on the Earth too, but because the Earth is solid, it doesn't stretch as much. Although it does stretch a little bit. Could be cause for some of the volcanic activity on the Earth, the tidal forces acting on the Earth, and maybe some of the other I don't know if you want to call it chaos happening on the planet. But anyway, the moon though pulls and has a larger effect on the liquidy parts called the oceans, etc. And so, depending on where the moon is, the water will kind of stretch out like an egg. So even on the other side of the Earth, it stretches out. So it's almost like, well, what's out here pulling it back this way? That's not really what's going on. It's just the water here and here is being kind of squished down because of the overall pull this way, which stretches out the water here. The sun also has a bit of an effect on the tides, but not nearly as much as the moon. And the moon goes around the Earth about once a month, yet the Earth spins once a day, right? So you can tell that the tides, first off, they'll happen twice a day because you get a high tide here and a high tide here, and then 12 hours later, this part of the Earth is over here, so you get another high tide again. But depending on where the sun is, if the sun is in the orbit here at one point in the month, then the sun will kind of will kind of pull out on here and minimize the moon's pull in this way. Whereas if the sun is over here in the same direction as the moon, that will the effect won't double, but it will be amplified, and you'll have even higher tides than normal. So that's kind of cool. Also because of the tidal forces, the Earth's rotation between the moon and the Earth, the Earth's rotation rate is slowing down. About 1 billion years or so ago, the day was probably about 22 hours long, a couple hours shorter. That turns out to be about 1.5 milliseconds every century. Every 100 years, the day increases by this much, which isn't much. We won't notice it over our lifetime. Another interesting thing is that we only see one side of the moon. That's because the moon is now tidally locked in with us because of the Earth's tidal pull on the moon, and so it spins the exact same with the exact same rate that it revolves around the Earth. 1 month it goes around, and 1 month it spins around. So we always see the same side of the moon. We had never seen the back of the moon until the Apollo astronauts went behind the moon. So that's pretty cool. And that's going to be it. I'm going to talk more about the moon, obviously, in the next 2 or 3 videos. But that's a pretty good overview of the Earth. And if you're more interested in the Earth, take a geology class or look up any textbook that talks about the Earth. But we're going to move on. All right. Thank you. Talk to you later.